We'd like to welcome you all today to the Water Talk Seminar Series. Today we have Mr. Stan Smith. Stan is a PhD student here in the mathematics department. He received a BS degree in chemistry from Rocky Mountain College in Billings, Montana, and then moved over to Bozeman, Montana, and got an MS degree in chemical engineering at Montana State University. From 1982 to 1986, he worked at the Idaho Chemical Processing Plant for Exxon, Nuclear Idaho Company, and Westinghouse Idaho Nuclear Company. If you don't know where that is, that's around Idaho Falls. It was my old territory, so I was just talking to him about it a little bit. And since 1986, he's been working on his PhD in mathematics under the direction of Myron Allen in mathematics and Jay Puckett in civil engineering. Today, he's going to talk about efficient groundwater drawdown model using finite layer method. So, Stan, all yours.
Thank you. What I thought I'd do today is present a brief summary of how the method is developed and show some preliminary results of the application that I've been doing. The overall objective of the current research under Myron Allen and Jay Puckett is to model a confined multi-well aquifer using this finite layer method. There's a few things to note. This is a several aquifers here. There's a few aquifers that are fully penetrating throughout the whole layer, and there's also a partially penetrating aquifer. The partially penetrating aquifer is the rather difficult thing that we'll have to deal with. Today I want to emphasize that I'm only going to look at two basic problems: a spherical conduction type problem and the fully penetrating case, in order to make movements toward the multi-well case. The major assumptions is that the aquifer be a confined aquifer. That is, there are no flow boundary conditions on the top and the bottom. There might be several layers within this particular aquifer. That's known as the confined aquifer. I also assume that Darcy's law is applicable and that hydraulic conductivity is a step function of elevation only. That is, I could layer this particular aquifer into several layers if the hydraulic conductivity changed. The first problem I will look at numerically and compared to an exact solution is the single fully penetrating well. A few things to note. We've got horizontal flow into the well. I will also use a constant Q. The well penetrates throughout the aquifer. We have no flow boundary conditions at the top and the bottom. I will also, in this particular case, just deal with a single hydraulic conductivity so that the properties throughout the aquifer are the same. The exact solution is readily available, the Similarity Solution. The second problem that I will look at numerically is the spherical conduction problem. This is a little more complicated. Once again, I'm going to assume that the aquifer has a single hydraulic conductivity. Once again, impervious layers on the top and the bottom. This could really be thought of as a heat conduction problem where you've got a point source and you're applying a constant flux. And the temperature, of course, conducts, or the heat conducts outward, and you get a temperature profile. In hydrology terms, it'd be like a point source where you're injecting at that particular point in the aquifer a certain flow rate. This will be the second problem that I look at. I also want to note that because of the nature of the problem, I have to divide this aquifer up into layers. I will use more layers around the point source where there's more flux, and a labeling that I will use is a nodal plane. The very bottom layer is a nodal plane. The very top is the impervious layer is the nodal plane Zn plus 1 if there are n layers. In this particular case, there's 1, 2, 3, 4, 5 layers. This particular plane would be nodal plane Z6. That's the terminology I will use. Well, with that out of the way, we'll go to the governing equation. A few things to note about the governing equation is that I didn't put it in terms of transmissibility. I kept it in terms of hydraulic conductivity. And the main reason is that I wanted to allow hydraulic conductivity to change as a function of elevation. The hydraulic conductivity in the x and y directions can be different, but in horizontal planes they will be the same. You'll have the same characteristic in that horizontal plane. Of course, I use specific storage rather than the storage coefficient. The forcing function is what I will use to introduce the point sources or a recharge boundary. This is really the Poisson equation and as I work with it. A typical domain, it will be a finite domain. Here I've labeled the particular nodal planes. The bottom plane will be Z1. The top plane will be Zn plus 1 if there's n layers. And a particular plane in the middle might be nodal plane Zj. It is finite in nature. To really get into the method, you need to review the Fourier series. If I considered a function of this type, where it's 1 between minus x and 0, go ahead and draw that in, and 0 at this point, and 1 here, just a function. And then if I allow it to repeat periodically, I can approximate this particular function with a Fourier series, which can be written in terms of the sign. H of x is equal to the sum Cn sine n pi x, where the Cn is derived by the integration throughout your domain. And in this particular case, these are your coefficients. This is a unique representation of this particular function in the Fourier series. Things to note, notice that the coefficient as n becomes large gets arbitrarily small. Another thing to note is, well, this is the function written out. Another thing to note is that we can approximate this function by truncating the series. And this is what we will do in the method. For instance, here's this function again, minus 1 and 1. And I'm going to approximate this particular function with just one term in the Fourier series. If I wanted to get more accurate, I would just continue to add more terms. This is with two non-zero terms. Notice that I am much more accurate in the vicinity of the function. And if I wanted to go on for 9 terms, actually 5 non-zero terms, you can see that you get even more accuracy. This is the same idea that I will use in the finite layer method. Only instead of the one-dimensional case, you can say the same thing about the two-dimensional case. You've got an xy plane, you've got a two-dimensional domain, and a function or a surface above that plane. You can approximate that, or you can actually write that function in terms of some basis function and a coefficient in an infinite series. For example, I might estimate or talk about my function h of xy in terms of a double sine series. Notice the multiple subscript on my coefficient. That's to enable to handle both sums in the x and the y. It's a double series. I can also approximate this series by truncating. And instead of going to infinity, I will go stop at 100. Or maybe I will stop at 30 for each of the m terms or the y terms. I should also mention that in this approximation, this particular phi, we will also come up with a way to obtain that phi. That is unknown when we move into the method. So going back to our domain, our aquifer, I will take nodal plane ZJ, and you can think about just sliding it out. And on that particular nodal plane, it's got a function of head. And I will estimate that head, it's a function of x and y, in terms of this Fourier series. I also included a j in here to indicate that that's for that particular plane in your aquifer. I can approximate that function by truncating the series. And that's precisely what we do. The question is I should leave that up there, what happens if we aren't on a nodal plane but somewhere in between? So we have to come up with a way to handle that. Well, one nice way to handle it is just to simply use linear interpolation. Here's an approximating function. It's a function of x, y, z. And I'm going to write my coefficient as a function of z. And I will obtain that by simply linearly interpolating between the two node planes and just coming up with a coefficient. I should also note at this time that in order to get time into the problem, as time goes on at a specific time, there's a specific head, I will also allow my coefficients to change with respect to time. This is how I will work through the problem. So what we have is the differential operator, the partial differential equation, and a method in which to approximate the head. At this time, these phis are unknown. We do not know what those are. This is our basis function. It might be a double sine series, like I showed in that double Fourier series. So the question is how do we determine the phis, the phi mnj? Well, we'll use the Galerkin finite element method. And I'm not going to go into too much detail there other than say basically what it's about. I apply the linear operator to the approximating function that we've come up with. And this, of course, is our partial differential equation. I will multiply it by a weighting function and integrate over the whole domain and set it equal to 0. And what you will end up with is a linear system with the phi mn j's unknown. In the Galerkin sense, the weighting function is really just the basis functions used for your approximating polynomial, or your approximating function. In this case, we used a linear interpolant in z and a double sine series in x and y. And that will be our weighting function. What we do, this is a sum. We will interchange the integration and the differentiation with the summation. We will go ahead and differentiate. We will go ahead and integrate. And that will set up your system. The real key to the finite layer method is the orthogonality of your basis functions when you integrate. For instance, if GMN is our double sine series, if I were to integrate G with two double sine series with different coefficients, you will end up with 0. And when you integrate, you lose a lot of your terms. In other words, you'll end up with a very sparse system with your matrix is concerned. Similarly, if you look at the other parts of the differential operator as you apply it and integrate it, you will lose a lot of your terms, and you'll end up with a very sparse system. So upon integration, what you end up with, instead of a large linear system, you end up with an mx by my small systems. In other words, for each mode, you will end up with its own little problem. The problem completely uncouples. So you end up with a nice small linear system of dimension n plus 1 for each mode. And when I say mode, I mean for each mn. Now, in boldface, what I mean is the coefficient vector, where this is a vector of phi mn1, phi mn2, on the way up to phi mn n plus 1. That is the length of the vector. This is a nice linear system to solve. SK is the triangular mass matrix. It's triangular in this case because of the nature of the hydraulic conductivity, since we use step functions in Z. And we also use linear interpolance in Z. And you end up with a nice tridiagonal matrix. B is the stiffness matrix. It's also tridiagonal. A finite difference scheme is used to solve the time derivative as we start marching through time. The main benefits of the uncoupling is it's going to convert a rather large three-dimension in space sense problem into mx by my, where these are the upper limits of your truncated series, two-dimensional problems. Thus, what you can do is you can take each one of these smaller problems and throw it into a parallel computing environment. So each of the smaller problems are going to be handled by one of the processors in a parallel environment. Or you can, because these are smaller problems, you can put it into a microcomputing environment and solve one problem at a time. I will talk more about this when we get into the particular problems. Going back to the single fully penetrating well, the actual numbers that I used, the depth of the aquifer was 100 meters. I went ahead and converted to transmissibility. It's 400 square meters a day. The storage coefficient, I used 1.6 times 10 to the minus fourth, and a constant discharge Q of 1257 cubic meters per day. The number of terms I used were approximately 900. In other words, mx and my were essentially 30. So 30 times 30 is 900 modes. If I didn't use the finite layer method and just simply solved the system, or if I didn't have orthogonality, I would have 900, and I used only one layer, so there's nodal plane 1 and nodal plane 2. I'd have ended up with approximately 2,000 dimension linear system. With the finite layer method, instead, I ended up with 900 2x2 systems, two-dimensional systems, which in this case was quite an overkill. The similarity solution exists for that. I will just point out what it looks like. This can be found in most of the hydraulic literature, or the old hydrology books. It is just a similarity solution. The actual comparison of the model with the exact data for the number of modes I took, I did really overkill it. These constitute 3 time steps, one at 14.4 minutes, one at 28.8 minutes, and one at 43.2 minutes. The line itself illustrates the numeric solution, the finite layer method, and the x or the 0 or the plus represent the exact values using the similarity solution. And as you can see, the similarity solution essentially falls right on the numeric solution. I did use plenty of terms. I did not probably need to use so many terms. But for the fully penetrating case, it worked real well. This, by the way, is the radial distance from the source. For the spherical conduction problem, I left it in terms of the hydrology units. I used a thickness of 32 meters, transmissibility 6,250 square meters per day. The specific storage, I used 1, and I used a constant discharge of 2,010 cubic meters per day. This down here represents the analytic solution. It's an error function. I should briefly talk about if I did not have orthogonality and just solved the system, this would be about a 50,000 length vector or system to solve. Because of the orthogonality and because we were able to uncouple each of the modes, we ended up with a 900 51-dimensional linear system. A 51-dimensional linear system can be run very nicely on a micro, and a 50,000 length system might be rather difficult to run. Same way in a parallel computing environment, you can start running the 900 individual problems one right after another because it is completely uncoupled. My data, let me pull this back in real quick. My data is going to represent the head values as I go up the z direction in elevation as I get away from the source. And hx will represent going along that bottom nodal plane. So I will show two results in this case and compare it with the exact. This is a function of head with elevation and the exact solution. The time is 28.8 minutes from the start. As you can see, after 3 meters from the source, you're essentially right on the line. When you're real close to the source, even your exact solution, you've assumed a few things about your exact solution. I mean, you're assuming a point source, and as you get closer and closer to 0, your, quote, exact solution is shooting up to infinity. So you've already made some approximations with your model. The curvature with the numerical solution is more of a numerical smearing, an averaging out over those first few nodes. This is essentially the same thing, only at a time of 57.6 minutes on down. Once again, I've got a little bit of smearing. The exact solution is shooting up to infinity. And beyond 3 meters radial distance, you've got a fairly accurate model. Now this is with elevation. Moving on to head as a function of the x direction, or actually r in this case. As I move away from the source along that bottom nodal plane, once again, the numerical solution and the exact solution are in essence indistinguishable. Now this makes sense because this is really the double sign series. And I've used 30 y terms and 30 x terms in essentially 900 terms in my Fourier series. So it will be very accurate. And it makes sense that that's what you'd end up with. I have a similar result for the 57 minutes. The future research emphasis, one of the problems we have is, with the type of problems we're dealing with, is that the domain, the boundary, starts causing some effects. Now, we started with an initial condition of 0 head throughout the aquifer, and we imposed 0 boundaries. Well, in order to get an accurate account for early time, we had to take those boundaries out quite a ways. In the single penetrating case, we were out around 1,200 meters. It was a 1,200 meter square. So the thought is, and as time goes on, you're going to start losing some of your accuracy with your model because of the interference with the boundaries. So one of the ideas to handle that difficulty is to get it back to a nice finite domain is to solve the larger problems, calculate what type of recharge you'd need to supply the fluid into your finite domain, and then, in essence, work the problem with a no-flow boundary condition, whereby you will recharge the boundary to maintain the flow going into the system. This way it would be it is a finite dimensional problem. And we can take it for longer and longer periods of time. The other problem that's rather interesting that we'll need to look at in the near future is the partially penetrating well. The problems with this is that we no longer have horizontal flow. We've actually got flow that moves vertically as well. And because of this, we will have to divide this domain up into layers, like we did with the spherical conduction problem, and try to rework the problem. There are some analytic solutions for this particular problem as well. In summary, we've used the finite layer models to model the fully penetrating well and the point source conduction problems very accurately. It is also very efficient in a parallel computing environment, or it could be efficient, I should say. I have not yet really sat down and ran it in a parallel computing environment. However, I had to solve my spherical conduction problem on a computer bigger than the micro to get the whole problem in. I could run it in a microcomputing environment if I would write each of the smaller problems out on a disk and bring it back in. So it can be done on a microcomputing environment. And the future emphasis will be on the partially penetrating well. And then I've got one three-dimensional picture to indicate this is your XY. This would be like one nodal plane, and your point source is right in the center, and this would be the value of head as you go throughout the plane. Is there any questions?
First question is regarding the equation. And you said your equation, the only boundary conditional equation is the no flow on the top and bottom, right?
That is correct.
Okay, and
I should say in the finite layer method I used zero boundary conditions and actually made it a finite domain on the boundaries, on the XY boundaries.
The side boundaries.
On the side boundaries.
Okay. I thought your side boundaries, your side boundary condition is the periodical one. No?
No.
Okay, I see. And also, you write down your solution in a series form, right?
Right.
Now you take the first 30 or 50 moves. And when you approximate your solution, you just approximate in the z direction. You discretize your the phi, which is the coefficient of the double side function, right?
Right.
So essentially, and this is a one-dimensional problem because the double side function are orthogonal.
Right.
Right. So that's why you said it can be done in parallel way. And so my question is this: when you approximate the coefficient phi, and you have a parameter h,
Right.
in mesh size, right? And that means you should have an error estimate in terms of its h and also in terms of the number of modes you used.
Yes, eventually we will be working toward those type of estimates. This is more of the application aspects of the problem. The more mathematical, theoretical aspects we will be getting into.
Right, because the estimate will, in one hand, depends on the number of modes
Right.
and also the mesh size.
Correct.
And okay. Yeah, that's all my questions.
I believe if you do have questions, if you could push the red button, and it can be recorded. Any other question?
Stan, there's certain geometric limitations involved when you do this discretization in this way, where you have finite elements in one direction and Fourier series in two directions. Maybe you could say something about how you might, for example, have finite elements in 2 dimensions and, let's say, Fourier series in one direction, or if there's any variations along those lines that might be useful.
Yes, there are. Let me go back to a typical domain. I do want to say that one reason that we went to the nodal plane idea, where we had a 2-dimensional Fourier series in the x and y, is the nature of the problem. Typically, an aquifer is layered horizontally with the properties of the aquifer fairly constant in that horizontal layer. And it is very nice to have a fairly accurate representation of the head on that particular layer. What does change, however, as you go in elevation throughout the aquifer, or maybe a multi-aquifer system, you need that flexibility to change your conductivity. And in using the finite element in the elevation, you're able to incorporate that into your problem. Now, what Myron suggested is to indicate that one could do a 3-dimensional Fourier series. These are your fast Poisson solvers, for instance. However, you don't have that orthogonality, because if you change your hydraulic conductivity with respect to elevation, you start losing that. You also could have just simply a line, and that could represent the Fourier series on a particular line, and then do a 2-dimensional finite element technique on the rest of the domain. It's rather hard to depict on here. But that's another possibility. Of course, the last possibility is to have a finite element method in 3 dimensions, which can get extremely large. And the whole idea of this particular method is to incorporate some of the nice facets of the Fourier series and the rapid solvers with a finite element to handle the varying layers.
I think you are able to solve a one-dimensional problem, and why not? I mean, this is much simpler, and you can solve it quickly, right?
That's correct.
I mean, as Maren said, this highly depends on the geometry of your domain, and otherwise you are not able to uncouple this equation.
That's right.
Okay, another just small question. Just try to understand your graph. And so you have the numerical experiments on 30 modes in x direction and 30 modes in y direction. And what is
Right.
your h, and how small the h is?
Okay. What I should say is if I use 32 modes, this is in a frequency domain. And if I were to convert that to the real-time domain, then that would, in a 64 by 64 square, a 32 mode by 32 mode would transfer into 2 meters. So actually, how I solve these are I use a fast Fourier transform to convert from the frequency domain, which is the modes, into the real-time domain, which is the what you're talking about, more of a mesh, more of what you see here is more of a. So really, what we're dealing with is you're really at liberty to pick the number of modes, and the way we go about picking the number of modes is that we go until the coefficient is a particular tolerance, till the coefficient is small. Of course, you're always running the risk that out there you've got another dominating coefficient, in which case you are wiping out some of your detail in when you convert it into the real-time domain, real space domain, I should say.
Yeah, I think the key point is that you can check convergence on the fly. You don't have to set the number of modes a priori. Okay, if you have a particular aspect that you're studying, that can be set or to some convergence tolerance, and then you can go on to the next time step.
You can continually calculate the new fees. You'd start with 1, 1, 1, 2, 2, 1, 3, 1, and go on out until finally you're out to 51, 51. And all of a sudden that's small enough that you decide that we'll stop here.
Kind of self-adaptive.
Right, if you want to make it self-adaptive.
Yeah.
Right. In which case, then you would pad it with zeros if you're using the Fourier transform ideas and do your inverse transforms. Yeah.
In that regard, maybe it's useful to say that for these kinds of problems, at least the ones we've looked at so far, the solution tends to get smoother and smoother as time progresses. So typically you can lop off the higher degree terms, higher order terms in the Fourier expansion and do fewer and fewer of these small parallelizable problems as time goes on.
Right. After 3 days in a particular model, after 3 days, you might only need 3 terms, and you've pretty well modeled your problem. That might be exaggerating, but your more dominating terms are up front, so to speak.
Okay, if I understand what Maren said is because this function gets smaller and smaller, essentially you can enlarge your h, right? You can mean the h may not be very small because the solution is very small, and a big h can get you a fairly good.
If you jump from the frequency domain back to the space domain, that would be correct.
Right.
Yeah. Yes.
I have a question in regard to when you talk about multiple aquifers, are you talking about aquifers with different transmissivity or conductivity properties?
Right, and there might be an impervious layer in between them. Although if we get the partially penetrating case down, we might even be able to handle the leakage between aquifers.
Okay. Then I want to take that a little bit further then. And in your solution set, can you allow the head to vary between layers? Do you have to define that? You see, because as I think of a multiple aquifer system, I could have one aquifer that I've penetrated, and I've actually perforated the well in that aquifer. Then I go through a confining layer into another aquifer. And what happens is the heads in the two aquifers are not the same.
That's right. That's a similar case with the partial penetrating case. As you go down along your well, the value of the head will change. So if you can handle the partially penetrating case, you would just simply move it into the multi-aquifer case and handle it in much the same way. As far as we can tell, it's going to be an iterative type procedure to obtain the heads that you need to obtain a constant flow out.
Okay, well, that was where my problem was coming in. I was wondering if this type of a technique then would handle the situation where the heads in one layer up here and were different than the head layers down here, and perhaps not only are you getting flow to the surface, but you are also getting flow into the other aquifer.
Yeah, that's
Will it
fine.
handle that type of a situation?
It'll be an iterative type situation. Yeah, I believe it will.
So that in the end we could tell whether we were contaminating the other aquifer if the one, as well as pumping water out
That's
through
quite
the system.
feasible.
It is quite feasible.
Yes.
In fact, Vic, what the three of us have, Jay, Stan, and I have kind of imagined is we could use a model like this in conjunction with certain well tests where you might put a balloon or something in the well to block flow within the well, and then do some sort of injectivity tests to test for vertical communication between layers. So you could have layers with different heads and different conductivities, and use the model in conjunction with the well test results to see whether there's actual vertical communication or not, which, you know, something that may not be apparent just by, let's say, doing well logs and that give you information in the immediate vicinity of the well bore. Now you could use well tests in conjunction with a model to quantify the communication between layers.
Well, the reason I was asking, because I mean that's a type of a problem that, you know, we can't solve now with finite differences, finite element techniques with just a straightforward solutions.
Is there any other question? Well, thank you.